Go on, please.
So do you see my screen?
Yes,
I
we do.
will warn you 5 minutes before finishing.
Okay, thank you. So good afternoon. I'm Oleksandr Pylypovskyi from the Greenwood Center in Dresden-Rossendorf in Germany and Kyiv Academic University in Ukraine. It's my pleasure to be at this event here this virtually, and I would like to thank organizers for this possibility and for all their efforts to bring all of us together today. I believe the topic of curvilinear antiferromagnets I will talk today is of special interest here, as a direction which was gone by the very good day at its start. This topic began with a bachelor and master thesis of Denis Kononenko, who is now a PhD student at the ETH Dresden in Germany. Our first one, curvilinear spin chains with antiferromagnetic exchange, has been published in 2020, where I would like also to note the contribution from Dr. Konstantin Yershov and Artem Tomilov. We dedicated this work to the memory of Professor Day, and I will talk about this work and our future steps in this direction today. Also, I would like to acknowledge the contribution of all my colleagues to works I will present here. This includes Hatzider and EFI teams in Dresden, theorists and computer scientists in Kyiv National University, and experimentalists in Basel. The structure of my talk is the following. In the introduction, I will tell why antiferromagnets are so interesting nowadays and what is curvilinear magnetism at all. Then, in the next two chapters, I will discuss the curvilinear spin chains, namely how the magnetic responses are changed by exchange and by anisotropy, which makes them so different from ferromagnets. And at the last chapter, I will show recent advances in experiments where geometry of the samples is crucial and how it can be potentially addressed in future. So we know that all materials possess some magnetic properties. For practical purposes, the media with ordered magnetic moments is of key interest. Of course, ferromagnets are studied most intensively because of presence of macroscopic magnetization. This simplifies visualization and manipulation of respective textures. Also, ferromagnets represent a small classes of ordered magnetic materials, while other ones have compensated or almost compensated magnetization at the atomistic level. The latter includes weak ferromagnets and plenty of antiferromagnetic materials. Such a complex intrinsic structure of media shown at the right-hand side determines the complex and interesting behavior of these materials for both fundamental and applied point of view. Depending on the number of sublattices, it's possible to introduce a few vector order parameters to describe the microscopic state of an antiferromagnet. Usually, we are interested in some anisotropic and chiral properties of the media to utilize them for practical purposes. They are determined by the local crystalline surrounding of the magnetic ions. By fine-tuning of their combinations, as well as utilizing magnetic multi-layer structures, it's possible to obtain the desired properties in some temperature range. This can be illustrated by the large family of the rare earth garnets, where, for example, the substitution of the conjugate ion changes the compensation temperature point. This tunes the saturation, magnetization, and behavior of magnetic textures. The key obvious features of antiferromagnets include a strong robustness against external fields and negligible stray fields. For example, they promise much denser placement of antiferromagnet-based memory units. Of course, at the same time, this determines all the challenges in visualization and characterization of antiferromagnets. The last decade is marked by the rise of antiferromagnetic spectromics. Electric and spin currents show the possibility to switch the order parameter using the current densities, which are significantly lower in comparison with ferromagnets. One of the key enablers of the effective manipulation by antiferromagnetic textures are Stargate torques. They arise in crystals with a locally broken inversion symmetry for magnetic ions. The multiple sublattices of antiferromagnets also enable a new physics at the microscopic level. This is pronounced in the high domain wall velocities in comparison with ferromagnets, and in absence of the Volcom breakdown. The Magnus force is a well-known inconvenience of ferromagnetic skyrmions. It pushes the skyrmion laterally to the ground direction. In contrast, the antiferromagnetic skyrmion in two sublattice antiferromagnet has a compensated Magnus forces in both sublattices. Nowadays, under the curvilinear magnetism at all, one understands the investigation of the interplay between the geometry and magnetic textures. It is well developed for ferromagnets. Let us imagine a curvilinear ferromagnetic wire or thin shell. In this case, the magnetostatics induces a specific shape anisotropy, which tracks the geometry. Also, ultra-thin films grown at the inhomogeneous substrate or sand via strain engineering possess the easy access of the anisotropy, which is normal to the shell surface. This shape or easy normal anisotropies allow the magnetic textures to know at what geometry they live and possess some geometry-driven features. First of all, this is geometry-driven symmetry breaking, leading to stabilization of the chiral domain walls at curvatures, even for the intrinsically achiral materials. The geometrical chirality of the Möbius rings or spiral is intrinsically coupled with the domain wall chirality and the broken symmetry of the anisotropic magnetoresistance. Moreover, this can lead to the appearance of imbiled skyrmions as ground states in ultra-thin films. Modern technologies such as FABIT or FIBIT allow to create nanoarchitectures of almost arbitrary shape at the micro and nanoscale. So, in other words, the approach of curvilinear magnetism opens a way to tailor the design, chiral and anisotropic responses even in intrinsically achiral materials. Another important consequence is to utilize the third dimension in comparison with the conventional formal electronics, which opens new physics and effects in magnetism. And here I would like to discuss what happens if we go from ferromagnets to antiferromagnets, which are extended in the third dimension, and what new geometrical effects we can get here. In the second chapter, I will focus on the exchange-driven phenomena in curvilinear antiferromagnets. The simplest sign of non-trivial geometry is represented by the boundary conditions. A ring possesses the periodic boundary conditions in geometry. However, the symmetry of magnetic lattice is dependent on the total number of spins. In the case of even magnetic moments, the antiferromagnetic nearest neighbor exchange leads to appearance of the Möbius state. Taking into account the uniaxial anisotropy and dipole interaction, it's possible to identify plenty of the long-living non-collinear states. Interesting to note that such states can be obtained experimentally, for example, in a large family of chromium wheels. Here, the geometric frustration was obtained by incorporation of the nickel ion. Depending on the engineering inter-ion exchange, the Möbius knot is based at the chromium or nickel ions. Let us consider the minimal model of the spin chain with the nearest neighbor antiferromagnetic exchange and the dipole interaction between spins cooled. The spins are arranged along the space curve gamma. Its shape can be completely described by two geometrical quantities, namely curvature and torsion. In other words, if one has an expression for gamma, then curvature and torsion can be calculated, and vice versa. One can design the curve gamma by definition of function kappa and tau. These quantities determine the local reference frame at the curve, namely the tangential, normal, and binormal directions. Here you can see an example of the helix wire with radius r and pitch p. The exchange splits the system on two magnetic sublattices, which are here shown by the blue and magenta colors. It's convenient to combine them into order as a pair of vector order parameters, namely vector of ferromagnetism and Neil vector. Here they are marked by m and n respectively. It's convenient also to describe such systems consistently using the same language for geometry and vector fields, which are living on it. Therefore, both fields M and N should be considered as function of the arc length S along the curve gamma. The micromagnetic transition from the sum of our spins to the integral along the curve leads to the following expression for the exchange energy. Here one can see the homogeneous and inhomogeneous term and the parity breaking term. The latter is related to the penalty on permutation of lattices once they are selected in the given chain. Within the long wave approximation, the ferromagnetic vector M can be considered as a slave variable. One can easily show that the non-zero local magnetization appears due to the dynamics of the Néel vector, non-collinear antiferromagnetic textures, and external fields. This expression is valid for the curvilinear spin chains as well. The key difference between the straight and curvilinear chains is that typically the Néel textures along the curve are intrinsically non-collinear. Mathematically, this can be seen from the expression for the magnetization vector. Because special derivatives involve the derivative not only on the components of Néel vector, but also derivatives on the basis vector, which are also functions of the arc length. This gives the following consequence. When the Néel texture is locally homogeneous, there is the following local magnetization, which is proportional to the curvature and torsion of the given geometry. Exclusion of the magnetization can simplify the exchange energy functional. However, one should remember that these derivatives are taken into the curvilinear reference frame, and this gives far-reaching implications. The continuum Lagrangian for such a spin chain reads as follows. Here in the curvilinear reference frame, the exchange energy is split into the three terms. The first term has a form like a common exchange. It tends to preserve the uniform texture even in curved systems. Other two terms are determined by the geometry. This term is linear with respect to the curvature and torsion. Being a combination of the Lifshitz invariants, it reads as a geometry-driven and homogeneous Zolotchinsky-Mirror interaction. This is a source of chiral helomagnetism in curved antiferromagnets. And the last term here is bilinear by components of N and geometric invariants. It represents the geometry-driven anisotropy. The dipole interaction is responsible for geometry tracking by the magnetic system. One can show that in the continuum limit, it leads to the uniaxial anisotropy for the Néel vector with the hard axis along the tangential direction. A helix is the simplest space curve with a constant curvature and torsion. That's why it's convenient as a case study. Depending on the curvature and torsion, there are two possible ground states here. The first one is a homogeneous Néel texture along the helix. Here the green Néel vectors are in plane, which is determined by the tangential and by normal vectors. The in-plane direction is determined by the geometry-driven easy-axis anisotropy. It's important to note that the considered system has no other easy axis of anisotropy. This is different from ferromagnets, where the exchange-driven anisotropic terms should compete with the shape anisotropy, which is much stronger. The second state is periodic for the electron moving along the helix. It is determined by the geometry-driven Zolotchinsky-Mirror interaction and corresponds to the almost uniform texture in the laboratory reference frame. We note that both the states survive for any finite geometrical parameters like curvature and torsion. All these peculiarities of the Lagrangian are pronounced in dynamics as well. In straight spin chains, the spectrum consists of the acoustic and optical branches. The presence of curvature changes the acoustic branch to the low-frequency optic one. This is shown by the red lines for the sparse helix. In the analytical expression for the spin wave dispersion, the coefficients K0 and K3 play a role of the effective anisotropy, and D3 is the effective Zolotchinsky-Mirror interaction coming from the curvature. Large curvatures lead to the appearance of the region with a negative group velocity in the low-frequency branch. This is shown by black lines and corresponds to this dense helix. The depth of this minimum grows with the curvature and torsion. Here one can expect the possibility to form Bose-Einstein condensates for magnons. Important to note that antiferromagnet supports the dynamics which is induced by the special distribution of curvature. Each acts as a driving force. This motion can be characterized in terms of the collective variables approach with a pair of conjugated variables to be domain wall position and phase of the order parameter. The left image shows the equilibrium position of the domain wall at the maximum of curvature. Being shifted a bit, the domain wall starts to oscillate and the eigenfrequencies of the oscillations are defined for the position and phase. In the particular case of the parabolic spin chain, they are proportional to the 1.5 power and the square root of the maximal curvature of the parabolic spin chain. We also note that a similar picture can be observed in flat curves. They are characterized by the curvature kappa only because of strictly zero torsion. Therefore, the geometry-driven Dzieloshensky-Mirror interaction has only one term, determined by the curvature, and the anisotropy tensor simplifies as well. And in flat rings, for example, one has only one homogeneous ground state. Because of the strong influence of the curvature on the spin wave spectrum, here we have the picture similar to the helix. There are two families of low frequency and high frequency modes. Antiferromagnets are characterized by a variety of sources of anisotropy at the atomistic level. In contrast to ferromagnets, this can be pronounced at the microscopic level, for example, in the value of the spin flop field. And in the third part of my talk, I want to show that anisotropy can be also an additional source of the curvature effects, which can be important for antiferromagnets and ferromagnets. The inter-ion anisotropy is described by the Hamiltonian, which involves pairs of spins. The anisotropy axis is usually directed from the first spin to the neighboring one. It is the source of the local part of the dipolar interaction, spin-orbit coupling, and anisotropy of the exchange constants, for example. The single ion anisotropy is relevant for spins with large enough lengths and usually originates from the spin-orbit interaction. In the following, we will project the vectors of ferro and antiferromagnetism for each pair of spins on the first magnetic site in this pair. Since the antiferromagnetic order parameters always involve the pair of spins, the special variation of anisotropy axis necessarily is reflected in the energy. There are two consequences. The first comes from the single ion anisotropy and represented by the imagined homogeneous Dzieloshensky-Mirror interaction of the longitudinal type. We note that this term is not chiral by its symmetry and can be of importance in such inhomogeneous structures as domain walls, for example. The second consequence of the special variation of the anisotropy axis is the appearance of the non-diagonal anisotropy terms. This can be illustrated by the spin-flop transition of the flat ring. The spin flop itself is induced by the exchange-driven easy axis of anisotropy, which I have mentioned before. After the spin flop, one can observe the tilt of the net vector from the radial direction, which is proportional to the curvature. There is a tilt for the magnetization as well. And to summarize the geometry-induced change in magnetic responses, they can be divided into two groups. The exchange interaction comes into the game via the spatial derivatives. It leads to the chiral response linear by the curvature and torsion. The exchange-driven anisotropy brings about the easy axis, which determines the direction of spins in absence of the intrinsic easy axis anisotropy. The multi-sublattice intrinsic structure of antiferromagnets enables geometry-driven effects which stem from anisotropy itself. This includes the tilt of the in-plane easy axis, which is pronounced in spin-flop phase, and the homogeneous DMI of the longitudinal symmetry. At the moment, very few is done for the curvilinear spin systems with a dimension higher than 1. However, the nematic textures living on curvilinear shells are of theoretical and experimental interest. In particular, it was recently shown that they acquire properties similar to holistic liquid crystals. The nematic textures support highly inhomogeneous ground states on spherical geometries, which is observed in experiment as well. At the same time, they could be imagined as the twins of antiferromagnets in terms of the net vector only. Thus, one can expect that the physics of curvilinear antiferromagnetic shells could be even more rich and intriguing than in comparison with ferromagnets. Of course, any experiment is much more challenging than the theoretical investigation. However, there are first experimental steps, not only for ferro, but for antiferromagnets as well. And one can discuss the potential platforms for practical validation of such theoretical predictions. As in the case of theory, let us start from the effects of boundaries. Very recently, an interaction of antiferromagnetic domain balls with a non-trivial surface topography of the single chromium oxide was reported. The chromium oxide is a prototypical magnetoelectric antiferromagnet with easy exit and an air temperature about 35 degrees. The magnetoelectric coupling allows to induce a domain wall, which can be moved by the laser support. The stray field, which comes from the top surface of the single crystals, can be detected by the nitrogen vacancy magnetometry and clearly show the presence of the domain wall. Here, the surface of the sample is patterned by the rectangular mesas, as it's shown on the schematics. And you can see it on this topography. When the domain wall crosses the mesa, it possesses a strong tilt, which mimics the Snell law from optics. Interesting to note that this behavior is well reproduced by the minimalistic model of the chiral uniaxial antiferromagnet with two sublattices. The driving force to deflect the domain wall is exchange boundary conditions. They rotate the domain wall inside the mesa and produce a strong three-dimensional band, like it is shown on the schematics, which is extracted from numerical simulations. The interaction of non-linear textures with such topographic features highlights the elastic properties of the domain walls. The stain engineering is a well-established technique to transform the initially planar structures into tubular devices. It is widely used for non-magnetic and ferromagnetic multilayers. For ferromagnets, this allows to transform the perpendicular is the axis of anisotropy into the radial one, for example. Of course, it's possible to roll up exchange biased and antiferromagnetic films. However, this is yet to be explored. In absence of the well-pronounced magnetostatics, antiferromagnets possess its counterpart, magnetostriction. And it acts in a similar non-local way on the easy plane antiferromagnetic textures and lead to domains formation, which was partially discussed by Elena today. Here you can see a few recent examples of the strain-induced antiferromagnetic domains in stripes and nanodots. For lanthanum oxide, the objects were grown as a freestanding or embedded structures, which causes different directions of the easy axis due to the interplay between the strain and intrinsic anisotropy. The embedded stripes drawn by the ion implantation possess a transversal anisotropy, while the freestanding ones have the easy axis along the tangential direction, which is similar to the shape anisotropy. So the strain can be of key importance as for the geometry tracking interaction here. A promising direction of curvilinear antiferromagnets is presented by molecular magnets. The chromia wheels were shown at the beginning of the presentation, and here I would like to mention metallized DNAs. As it was reported at the ultra-low temperatures, the DNA with manganese atoms possess an antiferromagnetic-like long-range handling. Being stable and flexible, DNA molecules allow to design a variety of the so-called DNA origami shapes. This one can imagine them as a future platform for realization of quasi-one-dimensional antiferromagnets of arbitrary shape. Another possibility to design antiferromagnetic spin chains along the arbitrary planar course is provided by atom engineering techniques. Such objects can possess a strong enough anisotropy stemming from the substrate, which stabilizes the antiferromagnetic ground state here. In summary, I tried to sketch a state-of-the-art and some perspectives, including our contribution to the field of curvilinear antiferromagnetism, which we started with Eureka today. The link between the geometry and antiferromagnetic textures can appear by the various anisotropic and magnetostrictic forces. This enables a promising tool to tailor chiral and anisotropic responses of antiferromagnets using the geometrical curvature. At the moment, there is more or less established understanding of antiferromagnetic spin chains in the classical limit, and in 2 dimensions, exploration of the different types of lattices and exchange-based systems and multiplication is in progress. Partially, these results are summarized in our recent reviews. Thank you for your attention.
Thank you very much, Oleksandr. You actually, well, these 2 speakers have been a bit shorter time than expected. Very interesting talk. So we have time for questions, at least 5 minutes. Any question, please?
Larissa speaking.
Yes.
May I ask a question?
Sure.
Yes, Oleksandr, thank you very much. Would you please show the previous slide with the DNA and B and A form?
This one.
One before, with yes, this one with DNA. Do you think that the spin properties of the 2 forms of DNA have some biological relevance?
That's a good question. To be honest, maybe it's hard for me to comment, especially on biological relevance, but what I remember from this research, the pronounced magnetic ordering is in the DNA of this form. And such ordering of ions lost magnetic connection between them. So maybe if we want to utilize them for some biological reasons, we need this form of the DNA.
Okay, thank you very much. I will ask you to send me the reference to this paper. Thank you. Thank you.
Thank you. Do you have any more questions? So let me again thank you to the organizers